Hi, so I'm back. I'm going to skip ahead a bit now. I'm going to go through magnetic fields, the magnetic fields part of the specification, starting with magnetic flux density. This is essentially all about something called the motor effect. The motor effect is if you have a current carrying wire in a magnetic field, it will experience a force, therefore it will, accelerate according to force is mass times acceleration. So this is the basis of anything you have that uses an electric motor. So the fan in your computer, electric cars, electric blenders, hairdryers, anything you have that moves because it uses electricity to move, uses an electric motor. So it's quite an important kind of topic, if kind of, I think, slightly provided out of context in the specification. So the first thing you have to know is that if we have a current carrying wire, so here's my wire, my loop of wire, complete loop but nothing happening. If I join it up, as soon as I join it up, there's going to be a magnetic field around this wire, right, the whole way around this wire. So like if I could draw it the whole way around, you'd find a magnetic field of concentric circles getting kind of increasingly smaller. So I'm trying to do it in 3D. If you imagine this is my wire, right, so if this is my wire, this would be the magnetic field, yeah? So you could see the wire coming up to you, the magnetic field is going to go around it like that. Now, if I put this wire, current carrying wire, in an already existing magnetic field, so this here is a uniform magnetic field, magnetic fields always point south, a uniform magnetic field, then you would get a magnetic field around the wire, right? Use the right-hand grip rule to determine the direction of the magnetic field. So the right-hand grip rule says if your thumb is pointing in the direction of current, it's going to curve around as though you're pointing in the direction that your fingers are pointing in. So current always goes from positive to negative. So that's going to go that way through the wire. So this magnetic field will be curving around like that. Now you get a magnetic field around the wire that interacts with the magnetic field that already exists, and the wire experiences a force, right? So in this case it's positive and negative, so the current is coming down this way through the wire, and I've tried to draw it perpendicular. I'll show you a model in a second. Now we can work out the direction of this force and the value of the force. So to work out the direction, we use Fleming's left-hand rule, this one, right? So the thumb represents the motion or the force. The first finger, so I say thumb motion, the first finger field, which goes from north to south, so you point towards the south pole of the field, and the current, second finger current, which points from positive to negative. The other thing I've seen is FBI for force, magnetic field strength, current. So FBI, like, the American Federal Bureau for Investigation. But I think thumb motion, first finger field, second finger current works just fine. Now, so that tells us the direction that the wire is going to move. And I'll show you an example on this one. So I've kind of got my wire coming out, like my field's going this way. My wire's kind of coming out, like the idea is it's supposed to be coming out towards you. Again, it's really tricky to draw these diagrams, and they always are really hard to interpret. So first finger field, second finger current. So because my thumb is pointing upwards, this wire is going to experience an upwards force. Works best if it's perpendicular. If it's not perpendicular, you've got to resolve something. Now, the value of the force is given by the magnetic field strength, which is B, mag field strength. So kind of like how many lines there are. If I wanted to make this a stronger field, I would go ahead and add in more field lines. I'd replace stronger magnets, which would mean more field lines. The field lines aren't really there. Then I've got my current, so the magnetic field strength times the current times the length of wire. And this equation only holds if it's perpendicular, if the magnetic field lines are perpendicular to the direction of the current. Then there's this idea of that this unit here is Tesla. So force is measured in newtons, magnetic field strength is measured in teslas, current is measured in amps, length is measured in meters. The Tesla is then defined by this equation. So the 1 Tesla is the magnetic field strength that produces a 1 Newton force on a 1 meter length of wire carrying a current of 1 amp perpendicular to the field, and that's how we define the Tesla. Now, I made a little model just to show you what the motor effect is. This is my magnet model, which I'm going to use more importantly later on. So if I have a current carrying wire and I put it in this magnetic field, yeah, perpendicular to the magnetic field, it's going to experience a force. Now, my field is going from north to south. So if my current is going down through the wire, you're going to have the wire moving up towards you because of the magnetic field produced around the wire. If I flip the current, then the wire will move down. Yeah. So it's because the magnetic field produced around the wire interacts with this magnetic field, and that's, like I say, the basis for all electric motors. So it's pretty important. Right. That's it. It gets trickier.